All right, welcome to another meeting of the New Dynamics and Number Theory seminar. Thank you for waiting. And we are ready to begin. Manuel Hauke is here from Norway, and he'll talk about metric Diophantine approximation, moving targets, and inhomogeneous variants. Welcome.
Thank you, Dimitri. Thank you to all the organizers for giving me the opportunity to speak here. Thank you also for everyone being patient that my technical issues are hopefully resolved now. So today I will speak about metric Diophantine approximation, moving targets, and inhomogeneous variants. I expect most people here are familiar with concepts in Diophantine approximation, so I will be a little bit faster when we're talking about basics, but I still want everyone to get a little bit of the concepts. But let's go into what we're talking about. So I start with a brief introduction, what the main topic will be. So probably most of you are familiar with these sets, which are like essentially Diophantine approximation. So we are given an approximation function psi that has support on the natural numbers, and let's say it goes to 0, 1/2. There's not really a restriction. We could also take bigger values if we need to, but let's say for simplicity in 0, 1/2. And to take a more general approach than in other cases, we take a sequence in the real numbers. We call the sequence gamma, and so gamma might change from denominator to denominator. And now we look at the approximation sets that we know in the usual case. So we look at W of psi gamma as the set of all alpha in the unit interval, such that the distance to the next integer of alpha minus p over q by some shift gamma, which might depend on q, is bounded to psi of q over q for infinitely many p and q. So the usual setting you might be familiar with is where gamma is just constantly equal to 0. This is classical Diophantine approximation property. But we want to make it more general in the beginning, and then we will focus on different cases here.
But I'm confused about distance from nearest integer. Is this integer already p? Do you really have this norm? You need this norm signs, or is it just?
I think
absolute value.
I think in this case it should be equivalent. Yeah, it's equivalent in this case. In some cases, I will just say p is say between 0 and q, and then it might make a difference just at the boundary.
I'm just asking about the norm. The norm is the distance of this to some other integer.
Yeah, exactly. It's just that we can reduce it, saying alpha is in the unit interval. But we could also just take the absolute value here.
Yeah, I think it should be the absolute value because this p is already in business. You don't want another integer. Okay, anyway, let's continue.
I think it's equivalent. You could take a multiple of p plus a multiple of q.
But you want p plus gamma q over q be close to alpha.
Yes.
Or close to alpha plus 1. What
yeah, but this is equivalent. That's what I'm saying. I could always take p instead of p plus q.
Okay.
This is the same.
Okay.
But let's think with normal distance, no, without distance to next integer. That's definitely correct. And the second statement, a second set I'm considering here is where we have coprimes, or we can also say where we count each rational only once, so p over q reduced. And I will denote this by w prime to denote the coprimality condition. So I'm thinking of what can we say about the sets w or w prime. When are they equal to the whole unit interval? And when is the Lebesgue measure full or the Lebesgue measure empty? So in what I'm considering in this talk, we will always take alpha in the unit interval, or maybe in higher dimensions, unit cubes. So there is no manifold or fractal or something like this coming in. Alpha is always considered to be in a unit interval. Okay, so classically, as I already said, gamma equal to 0 constantly. We get the classical results in the homogeneous Diophantine approximation. So Dirichlet's theorem in our statement, or in our language translator, tells you if you take psi of q as 1 over q, then both sets W and W prime are equal to a whole interval. So every number can be approximated by this. And in the metric sense, you're probably also familiar with these statements. So for me, lambda is the Lebesgue measure. Khintchine's theorem, which was extended by Duffin and Schaeffer later, tells you that if psi is monotonically decreasing, the condition whether you have full or empty measure only depends on the divergence of a certain sum. So in Khintchine's case, this was just the sum of psi of q equal to infinity. And you wonder whether this is a typo here. But it's actually not, because if psi is monotonically decreasing, then the sums are of comparable size. So we can also put in the phi of q over q here. This is just equivalent. But I wanted to put it with the phi of q over q here to have the comparison, what is coming now. Namely, as you probably also know, is that if we remove the monotonicity assumption in Khintchine's theorem, then the theorem is actually wrong. So it fails to be true. But if we change to the coprime setting, so asking about W prime, then this is still true. This was proven by Kokolopoulos Maynard in 2020, and this was known as the Duffin-Schaeffer conjecture earlier. So given any function psi, it doesn't have to be monotonic, the Lebesgue measure of W prime is 1, if and only if the sum of the phi of q, psi of q, or q diverges. So far we treated the homogeneous case. And maybe some people are already like, why should I even care about non-monotonic psi? So I would like to spend 2 minutes on my motivation, why I actually care about non-monotonic psi here. So when I'm talking to civilians, the non-mathematicians, about what I'm doing in my research, what is Diophantine approximation about, why do I need this, I'm always taking this example. So we're trying to approximate irrational numbers with rational numbers. Example, a computer has only finite capacity of memory, so we can't store irrational numbers by just writing all digits after the comma. So we have to truncate it at some point. And of course, we want to truncate it in a way that we can store the irrational that approximates it quite efficiently. So somehow we want to penalize large denominators because you can't store them efficiently. But if you look more closely, the large denominator might still be efficiently stored. If, say, the q is equal to 2 to the n, then you only need 1 bit. So in general, it could be efficiently stored if you have only a few non-zero digits in your binary expansion. And you want to measure this versus the approximation quality, which means you would like to have psi of q being quite large in comparison to other q's if q has only few non-zero digits in the binary expansion. But of course, this is like a highly non-monotonic function, psi. So this is my motivation coming from the applied point of view, but most of you are, as me, more in the theoretical world at home. So I would also like to give you an argument here. So if we take monotonic psi, then this helps you understanding the Kronecker sequence in alpha, irrational rotation. Already this is complicated enough that we don't understand everything right now, but we have a proper understanding of most properties here. But if we allow non-monotonic psi, then we can look at a special case of some of psi being non-monotonic. Namely, we fix some infinite subset A, And we consider psi of q as the indicator that q is in A times f of q, where f of q is, say, a monotonically decreasing function. So in this case, this helps us to understand Diophantine approximation with restricted denominators, or in other words, we can understand the dynamics of A and alpha, where A is an integer sequence. And I probably don't have to tell you that this has many applications, both in number theory, but also if we're thinking in a Diophantine approximation way, where we can ask Littlewood questions, where this AM might be some convergence to some other number or similar. So my main motivation is this, where psi of q is the indicator times f of q, where f of q is nice. And it somehow turns out that it's not much easier to consider only this special case. So we can't really say much more if we're only considering such psi, where the non-monotonicity comes from the restriction on the support. So we'll just consider arbitrary psi. But if you don't like arbitrary psi, just think of this example, and maybe you can say more. I would be very interested to see some results that hold for such psi, but not for arbitrary psis. Okay, coming back to our actual problem, we stated everything in the homogeneous case. It seems like we understand metrically what happens there, what happens in the inhomogeneous world. So by inhomogeneous, I mean, I take the sequence gamma q to be a constant, but a constant is not equal to 0. In this case, Dirichlet's theorem already fails quite trivially. For example, take gamma 1 over 2 and alpha 1 over 3. Then the orbit of an alpha will always be 1 over 3, 2 over 3, 1, and it will never approach 1/2. So there is no way to inhomogeneously approximate 1 over 3. But in a metric business, the theorem still holds. So Khintchine still holds for any fixed irrational shift, or any fixed gamma, rational or irrational. This was proven by Süß in the 50s. And as in the homogeneous case, Khintchine's theorem without monotonicity fails for every gamma. So this is like stronger, saying that regardless of what gamma I give you, I can find a counterexample. So clearly the question arises whether a Kokolopoulos-Maynard type result, so Duffin-Schaeffer conjecture, holds in this case. For gamma equals 0, we know it does. So what is the correct translation now from the homogeneous world to the inhomogeneous world? In this case, this is something we have to clarify here. So an immediate way to do this would be saying, okay, I'm giving an irrational or rational not 0 gamma. I'm giving a psi. Do we have full measure of the coprimes if and only if the sum of the phi of q's diverges? But I would argue this is somehow a little bit ill-posed. It might still be true. I'm not saying that it's wrong, but it looks somehow unnatural. And why is this? Let's take gamma to be an integer, say gamma equal to 1. And if we now look at the set, then we're trying to approximate alpha with p over q, where p minus 1 is coprime to q. This seems unnatural, and I'm not sure if it's actually true. And it has a strange phenomenon that it depends on the integer part of gamma whether some statement is true or not. And this is something which we shouldn't have in Diophantine approximation. We should always have something that depends on the Diophantine properties of gamma and not on its integer part. So the more promising approach for me is the slightly more technical looking statement I'm having here. So we fix the gamma, and then we want to take sets SQ gamma. So it sets SQ out of 0 to q minus 1 that might depend on gamma, which are of size phi of q, so that the Lebesgue measure here is 1 if and only if the sum of phi of q over q diverges. And in this case, we have the same set as before, but the restriction is not that P is co-prime to Q, but P lies in this specific set, which is of size phi of Q. So if gamma is equal to 0, we just take the co-primes, we know such a result exists. And now the question no longer depends on the integer part of gamma, because we could just say, okay, if gamma is equal to 1, then we shift SQ gamma just by the one integer, the co-primes, and we are back in the case. So this is the slightly more technical looking statement, but I would say this is more or less the proper way of trying to generalize this to the inhomogeneous world. And clearly, if our restricted set has full measure, then our set W has full measure, so we also get a sufficient criterion for the full measure of W without any prime or any restrictions. But of course, this is only a sufficient criterion. Might be that it has still full measure, but the sum with the phi's converges. We can't say anything about this because we have the counterexample. So it's not completely satisfying, but it would be nice to have anyways. Okay, so what I already mentioned is that if gamma is equal to an integer, then we get our statement for free by just applying Kokolopoulos-Maynard's theorem by the shifted coprimality thing. So a typical next step is looking at gamma being irrational, but not an integer. This is a result I established with Victor Beresnevich and Sanju Velani this year. So given an irrational gamma, then there exists sets SQ depending on gamma, such that we have this dichotomy. And in this case, our sets SQ gamma have a slightly different coprimality condition instead. Namely, we have BP plus A coprime to Q, where A over B is equal to gamma. So in the case where gamma is equal to an integer, or say 0, this just is the same as the typical coprimality assumption. So it's like a generalization of the theorem of Kokolopoulos and Maynard. And if you know how it behaves with rationals, you can go quite easily to looking at congruence conditions in the homogeneous setup. So we take arbitrary values RT as U, an arbitrary function psi, and we want to have a divergent along an arithmetic progression Q congruent S modulo U. And in this case, we get infinitely many solutions to the approximation that satisfies not only Q equivalent S mod U, this is like trivial because we restricted our psi there, but we can also say A has to be congruent modulo R modulo T for arbitrary values R and T. So this is really just a corollary from the rational case. I will not give you a proof of this, but it almost immediately follows from the rational case. So the next thing after establishing a rational case is obviously trying to push to irrational gammas. And the irrational gammas, the first that comes into mind to proving is either badly approximable or very Liouville, because these are the most extreme cases and you can try to prove something there. And in our case, it turned out that Liouville is the way to go in this sense. And the statement we're getting is a little bit weaker. So what we're getting is, if we're given a function psi, then we can construct a Liouville number gamma such that we can find sets such that this dichotomy holds. So why is it weaker? We can't construct the Liouville number gamma first, and then we take every psi that we want, and this condition holds. This is something we can't establish, but at least we can find for every psi such a number. Note that if you're given a psi, you could also use some metric arguments to show that almost every gamma has such a property, but this of course tells you nothing about which numbers gamma there really are. And our construction is really explicit. So this is the difference. If you're given a psi, we can construct any rational number explicitly such that this holds. In this case, the set SQ gamma looks a little bit more complicated than in the rational case. So in this case, the coprimality assumption is that B times QK plus PK has to be coprime to QK, where PK over QK are the convergence of gamma. And the K chosen here depends on the size of psi of Q. So it's not very easy to state this in a proper way, what the sets SQ gamma look like here, but we have a complete formulation of this. So we have a lot more of theorems that are somehow related to this, but the main technical theorem is the following. From there, everything I said before follows. So given some gamma, let us denote by pk over qk again the kth convergent, where if gamma is rational and has a finite continued fraction expansion, then we define pk over qk just equal to the rational point if k is larger than the length of the continued fraction. So assuming we can get infinitely many disjoint sets Sk, such that in this set Sk, we can approximate gamma by pk over qk with quality psi of q. And we accumulate enough mass in this Sk. So the sum of the measures in this Sk is greater than qk to the 8. Then we can prove our result. So for almost every alpha, we have infinitely many solutions where we have the additional assumption that bk plus aqk q, the GCD of this is 1. So if you look sharply here, the rational case follows immediately. So as I said, if gamma is equal to a rational, then pk over qk is eventually just gamma. So our first condition is just useless. It just holds trivially. And by assumption that the sum of measures diverges, we can always accumulate enough that the sum over the q's is greater than denominator of the rational to the power of 8. So this is an immediate corollary from here. And you can try to play a similar game with the Liouville case by constructing the next partial quotient after having accumulated enough mass that you get enough approximation quality. I will just say this vaguely, but this is essentially what we are doing. So as soon as you have accumulated enough mass, then you're trying to make sure that you approximate well enough, so you pick the next partial quotient just ridiculously big. That's the way you can construct the gamma here. Okay, so just a short word about the qk to the 8. This is 100% sure not optimal here. We could probably improve it very much, not only the exponent, maybe one could even show like a log or whatever. But the point is, we definitely need something that is growing in qk to make our result work. So it would be nice to have something like this without the assumption that the mass has to grow here, but we are not able to achieve this. Okay, just some short words about the proof sketch here. So as always in metric Diophantine approximation, at least if we try to treat it classically and not with dynamic methods, we're trying to get some variance estimate. So we look at the approximation sets for a fixed denominator q, and we want to get a variance estimate, which is also known as overlap estimate, since we're just counting the measure of intervals that are overlapping. So what we want to do is to prove for some constant c that we have quasi-independence on average. So the sum of the overlaps is bounded by a constant times expected value squared. And then we can apply some refined divergence per Alcantara lemma. In this case, we could take the Eder-Cherney formulation of this lemma, which implies that if we have such quasi-independence, the Lebesgue measure is greater than 1 over c, where c is the constant from the variance estimate. And in many cases, we have some zero-one law here. So this is coming from ergodic theory or from Lebesgue density theorem. And we have this in the homogeneous world. So for the non-coprime case, it's Castle zero-one law. In the coprime case, it's Gallagher zero-one law. So this tells us that the Lebesgue measure of the approximation set is always either 0 or 1. And since we already know that the Lebesgue measure is greater than 1 over c, which is greater than 1, it has to be 1. So this is the way to go in the homogeneous world. But unfortunately, we don't know any 0-1 laws in the inhomogeneous setup. So we can't lose a constant here. Or actually, we can, because we found a way to circumvent the 0-1 law here by employing an additional assumption, which is truly satisfied in our case. So what our theorem, which can be seen as a Borel-Cantelli type result, tells us is if we are given an arbitrary probability measure p, we have no assumption on everything here, anything here, and we assume the sum of the probabilities of some events to diverge. And we have some quasi-independence. So there exists a c such that the equation 1 holds. And we have another condition here, which you can think of as being a mixing condition. So you fix the r, then you take the q and send q to infinity and look at the dependence of the events aq and ar when q tends to infinity. And if this is in the lim sub smaller equal to 1, the events are independent or negatively dependent on each other. And if we have this kind of mixing condition, then we can ensure that the lim subset has full measure. So I stated it in a simplified version here. We can weaken the mixing condition a little bit by just having this condition on average. But for simplicity, let's take this condition here. And condition 2 is trivially satisfied in all statements we are considering here. Since AR is just a union of intervals of a fixed length, since we fix R, and AQ is a union of intervals that are much smaller since Q goes to infinity, you can approximate every interval of fixed length clearly by elements from AQ, since our elements A over Q, where A runs through the reduced residues, say, are uniformly distributed. So you get this condition 2 of 3. So you only need to show condition 1. And this is not...
Sorry, Manuel.
Sorry, was there a question?
Do you require condition 1 to hold for every capital Q, or is that also like a...
For Q sufficiently large.
Oh, okay.
And you could also, there is also a way of saying this only holds in blocks. So there's these two statements in the Borel-Cantelli case. So you could always have like smaller threshold as well. So if you have infinitely many blocks such that you get in the blocks this local quasi-independence, then this is also enough.
So usually the first condition is only required to hold for infinitely many capital Qs.
Yes. Yeah, I think infinitely many should be enough. Yeah, you don't need it for all. Sufficiently large, infinitely many Qs is enough. That's correct. Yeah. But I think in our cases this does not give an advantage, but in some cases it could. That's correct. And of course, as I said, this is like an arbitrary probability measure, so it could hold in every other setup as well. It's not specific on Lebesgue measure or unit interval or Diophantine approximation, so it could be used in any setup. Okay, so this circumvents the CR1 law, so we are left in proving quasi-independence on average, and there we have to dig into the technical details. I'm just going fast over this because I think I'm already a little bit after my schedule. So classical results on the overlap estimate are known since many years, since people tried to prove Duffin Schaeffer in the 80 years between the between the stating of the conjecture and the solution. So we basically know how the estimates look like. So in our case, we will treat the case where gamma is equal to a rational number. And here it becomes a little bit more difficult than in the homogeneous world, since we have to sum over some region smaller than some number that depends on several quantities. A function h of c, where h of c counts solutions where a and b are co-prime values in bq or br. A and b satisfy some equivalent, some congruence relation, and they have to be the solution to c over b times SEMQR. So there are a couple of statements here, but of course we have tools to tackle this. So in this case, it's sieve theory, and in particular sieve theory and arithmetic progressions. So this gives us some result. So if we're going back, we have here a quantity that we will denote by x, which is the length of the sum. So if the sum itself is quite short, then we can't expect much from sieve theory. So for example, if the sum is smaller than b, then we can't expect any cancellation coming from the congruence relation here. So the sum has to be at least as long as b to have anything meaningful. So this is why we have to split the cases here, depending on what the size of our summation here is. So if the size is very short, then we can actually have no overlap at all. But if the size is in between 1 and some value, which is b cubed here, then we just can't do anything better than just throwing away the congruence relation. And we get the expression here, which means we lose some factor b. And we lose a factor that's coming from the coprimality assumption. This is a classical factor that one loses in all of these Duffin Schaeffer questions. And if x is larger than b cubed, then we can win back this congruence relation. So the implied constants here are absolute, which means they're also not depending on b. We might think b is a bounded number, so it wouldn't play a role, but in our applications, we want to apply this for growing b's, so it's important to keep track of the constants here. So the implied constant here is really absolute, not depending on b. And the way to finish the proof, just a short remark here, is to say that the x on average is not too small. So it's a very rare event that x is very small. This is some generalized result from a paper I wrote some years ago with Christoph Eistad and Ben Border. And the factor that annoys us, the product of 1 plus 1 over p, is also bounded on average. So this is the key observation in Kokolopoulos-Maynard's result that solved the Duffin-Schaeffer conjecture. It has 32 pages, and this is a visualization in the original paper how to come to the proof. So what I call key observation here is proposition 5.4. So you can see all these propositions and lemmas going into this one key proposition, and it takes them 32 pages to prove this result. So I'm not talking about how they come up with this. If you're interested in how this is done, then I can recommend, again, my own work. Together with Elliot Walker and his PhD student, Santiago Vasquez, we did a simplification of their method. So we streamlined the argument, we strengthened it, and we did some shortcuts. And now the proof is 8 pages, and it doesn't mean we just increased the font size. It's really a genuinely partially new approach, which in my opinion really simplifies the proof. So if you're interested, have a look at this paper. Okay, so this is very shortly the proof how to come up with this rational and Liouville inhomogeneous Duffin-Schaeffer things. I would like to go to the moving targets now, but maybe it's a good point to have a short brief and ask if there are any questions about the results so far.
So if gamma is not Liouville, then you don't get anything from this method.
Then we don't get anything except we assume something like extra divergence. So this is something I didn't want to mention, but this also comes out of these results. So if I go back to this main technical theorem, if your psi gives you a little bit of extra divergence, then you can accumulate this mass quite early, say. Then you also get some results of approximation quality for other numbers.
If I remember correctly, there was a conjecture of Duffin-Schaeffer about coprime P and Q, and there was also a related statement about PQ which are not coprime and psi not necessarily monotonic. And
you mean maybe Catlin's conjecture?
Catlin's conjecture, yes, that's right. So
yes.
So I think Catlin's conjecture is something that is natural to try to generalize here, because you don't need any coprimality or no need for this SQ gamma.
Yes. So what I think is the proper way of seeing Catlin's conjecture in the inhomogeneous world is something I call weak inhomogeneous Duffin-Schaeffer. Is you have like an extra divergence with phi of q over q, but you still want to say something about the original set.
But Catlin's conjecture, isn't it about necessary and sufficient condition?
Yes, but this is equivalent to what I just said. This is proven, I think, by Felipe. That this is equivalent. Catlin's conjecture is equivalent to what I just said.
Okay.
That's why I think in the inhomogeneous world we should think about this weak inhomogeneous Duffin-Schaeffer conjecture, because Catlin's conjecture with the supremum condition again doesn't really make sense if you just try to translate it one by one in the inhomogeneous world.
It should be maybe different depending on gamma.
Yes, exactly.
Okay.
Any more questions so far? Okay, then I'm going to the moving targets. So moving targets means what I introduced in the beginning. Looks a little bit weird, but now it makes sense. In this case, our inhomogeneous shift is not fixed, but it's allowed to move with every denominator here. So I'm thinking of this like as in a computer game, the gamma q is something that is running somewhere around, and you're the n alpha and you try to catch it. Of course, the gamma q could be deviously chosen with respect to one fixed alpha. So clearly Dirichlet fails in a very bad manner. But you have the Lebesgue metric statement here. So maybe you can still catch it. But it turns out we don't know. So Khintchine's theorem for moving targets is, to the best of my knowledge, still open. I would conjecture this to be true. So with Felipe Ramírez, we conjectured this in our recent paper, but we have no clue about this. So by Khintchine's theorem, I really mean with monotonicity condition, but having a moving target. So that's an open question. I'm not sure if dynamical methods could work here, for example, since we have monotonicity, maybe we can translate this. But of course, we have the moving target, which makes everything a little bit harder. So again, without monotonicity, Khintchine just fails, and it actually fails regardless of what sequence you're taking here. But interestingly, a Cocolobulus Maynard or Duffin-Schaeffer analog does not hold for moving targets. So what I did with Felipe Ramírez is that we constructed some psi and some moving targets such that the sum with the phi weights is divergent, but still the Lebesgue measure of the approximation sets is 0. So this gives you a hint that in the world of moving targets, it's not as easy as we would guess it is. And I would like to show you a short proof of this. This is really quite a short proof, I would say. So we need a short lemma, which you can probably prove in 10 minutes. So if you're bored of me talking here, you can try to prove this yourself. It shouldn't take more than 4 or 5 lines. So it looks a little bit like a Chinese remainder theorem type result. So we take all reduced fractions with denominator p and denote this as qp prime. If p is square free and we have a divisor q of p, then we can decompose the co-prime fractions in the way that we sum up pointwise the sets q prime plus q p over q prime. As I said, very easy to prove, but quite powerful here. So the counterexample now goes as follows. We take P as the product of, let's say, the first L primes, where L is a large number, and take B as the set of all divisors of Q. And now we choose our moving target, gamma Q, in a way that gamma Q over Q is a reduced fraction in P over Q. And we choose the psi in a way that psi of Q over Q is equal to psi of R over R for all such elements in our set B here. And by our lemma before and this assumption on gamma Q over Q, which we can obviously do, we just move the reduced fractions of Q into the reduced fractions of P. And since the length of the interval, which is psi of Q over Q, is the same, we have moved our whole approximation set AQ into the approximation set AP. And this can be done for all Q in V. So actually the union over all Qs is just the biggest set AP. And this is of a much smaller order of magnitude than the sum of the measures. So we can construct this block and then we can construct another block and another block by a similar argument. And in this way, you can come up with the counterexample. But of course, we're using non-monotonic psi, we're using moving targets, and we'll use co-prime assumption. So it's not a hint about Khintchine's theorem being true or false in this setup. So this tells us, well, moving targets, maybe we can't say anything. But let's look at higher dimensions. Maybe we can say something here. This is like an obvious thing. If we can't say something in one way, let's look at something else and see if this holds true here. So short recap, Khintchine-Grosjev theorem, probably also well known to everyone here. We have a system of m times n system of linear forms here. And we want to approximate this maybe inhomogeneously. So we take some matrix alpha, multiply with a vector q, subtract p, and then we have a maybe moving target, maybe a fixed irrational number gamma, and we want to look at the approximation quantity here. So Khintchine-Grosjev tells you if psi is monotonically decreasing, that the Lebesgue measure is full or empty, depending on whether the sum of measures converges or diverges. This is just the sum of measures.
Wait, but was it proved so by Groshev? Was gamma not zero?
And no, with gamma equal to 0, it was proven by Groshev, and with gamma not equal to 0, I think it was Schmidt.
Okay.
So it's proven for every gamma, and I think it's due to Schmidt in the classical sense. So it's somewhere in the 60s.
Mm-hmm. And then probably some people, yeah, okay, that's exactly what you're talking about.
Okay, yeah. then some people ask about removing monotonicity. Can we allow our target to move, or can we do some Duffin-Schaeffer Cocolobulus Maynard analog, saying we have a coprimality in each component, we might get some phi value, can we do something here? These are the obvious questions I'm asking myself here. And it turns out in higher dimensions, we can do a little bit more than in dimension 1. So for example, if our dimension m, which is the dimension of the approximation of the is greater than 2, then the Khintchine, so with monotonicity, I mean with Khintchine, allows a moving target. So if m greater equal 2, then this is true. If m plus n is greater equal to 4, we can even remove the monotonicity completely in the Khintchine-Groshev result and allow a moving target. So everything is possible with the dimension is big enough. If we get a dimension that is closer to the case we are actually most interested in, where n equal m equal 1, then it gets tougher. So there is not much known about the cases where n plus m is equal to 3. So I obtained a partial result here. If our shift gamma is non-Liouville and fixed, so not moving target, fixed non-Liouville shift, we can remove the monotonicity in the case where n is equal to 2, m is equal to 1. And finally, a result I would like to talk about here, if dimension m greater equal to 3, we can also do a Duffin-Schaeffer-type result with a moving target even. So it wasn't even known for the inhomogeneous fixed target, but actually our argument doesn't need that this is a fixed target, but we can do it for a moving target. So what I mean here is our approximation sets have the additional assumption that we have component-wise pi coprime to q, and of course then the sum of measures gets another factor phi of q over q to the m. And we get a perfect dichotomy between the sum being divergent and the Leveque measure being full. So I would like just to give you some ideas about the proofs here. All proofs work in a similar fashion than I sketched before. So we do some overlap estimates. We apply some form of Borel-Cantelli lemma. And for the overlap estimates, we always have some kind of sieve theory problem to solve, which differs in the different setups. So this is what we have to care here. So first of all higher dimensional cases are essentially reduced to estimating one-dimensional overlaps. But the degree of independence we need in these one-dimensional overlaps gets smaller the larger the dimensions is. You can think of this being geometrically, if you want to avoid intervals in the unit interval, well, they might still overlap. But if you want to take two rectangles in the unit square, they have 2 degrees of freedom why they could avoid each other. So to get some independence here is a little bit easier. And indeed, it turned out also in the Duffin-Schaeffer case, for example, Pollington and Vaughan already proved in 1990, 30 years before Cocolobulus and Maynard proved the Duffin-Schaeffer conjecture, that in dimension m greater equal to 2, everything's fine. So our result is an analog of Pollington-Vaughan's result in the inhomogeneous world if m greater equal 3. So we are getting partially to what we want to do. So looking at the technical problem is we have a Sieve condition here. So we are summing integer points C in some range, and the range depends on basically everything here. And we would like to get some cancellation in that. We say like the number of integer points in here, this is a summation of length 2x. This should be bounded by up to a constant by x. And if we have another condition on C, then we have to also get back the probability of the condition. So in most cases, this is like a coprimality condition. So we would like to win back the phi factor here, but this could also be a different condition. So what we can do, like the quantities depend basically on everything. So we just do a trivial estimate. We count the integer points in an interval. Well, trivially, this is at most 1 point plus the length of the interval. And this sounds quite stupid, but we can't do much more actually. So in the non-reduced setting, we can apply this and look at the error. So the error that is coming in here is a GCD of QR times the minimal value. It should be minimum psi of Q and psi of R here. And if we go on here and the dimension is big enough, so in this case m plus n greater equal 4, then the error term we are picking up here is small enough. So we get some GCD sums. We have some ideas about GCD sums. And the error term is small enough. So we are happy. This, in a nutshell, proves the result from Manuel Ramírez that we can remove monotonicity with a moving target in high enough dimensions. Because the trivial estimate we had didn't see whether the target is moving. In the coprime setting, so in the result I established with Felipe Ramírez in high enough dimension, we have to win back this coprimality assumption. So we can still try to do like the trivial estimate in the way where the interval is based, but we have to incorporate the Sieve to win back the phi factor. And this can be done in a similar way than it was done by Pollington and Vaughan. We had to refine the estimates a little bit, but we can still allow this trivial estimate in the Sieve in the length with the 1 here because the dimension is big enough. So we can't push this argument any further because this just fails for m smaller or equal to 2. So this is in a nutshell the proof of the Duffin-Schaeffer conjecture in dimension 3. And in the end, I would like to go back now to what I started with, namely the inhomogeneous parameter gamma is fixed. We have no longer a moving target. What is the technical condition here now? So now we have to count integer points again in some range of length x, plus we have some shift that depends on gamma. So it's q minus r over GCD of qr times gamma. And we want to count integer points, and we only want to have at most x many. So the problem is apparent if x is really small. Like if x is bigger than 1, then we don't care about the 1. So if x is small and we still get an integer point, then this is problematic. So in 1 minute, why my proof of the non-Liouville case worked is that if my parameter gamma is non-Liouville, then the distance of q minus r over GCD qr gamma is bounded in distance to the next integer norm somehow away from 0. So if the length of the interval x is smaller than this, then we actually get no integer in this sum at all. So in this case, we can just bound this by 0. And it turns out that this is the critical region where the x is so tiny that this fails, and otherwise our arguments are good enough. So this suffices to prove the case where n is equal to 2, m is equal to 1, in the case of non-Liouville numbers. But of course, here we need to have a fixed target and a non-Liouville target, because otherwise we can't make such an assumption. And for the open questions, meaning like inhomogeneous Duffin-Schaeffer conjecture or every kind of type we discussed before, we probably have to be a little bit more clever here. So we need to get some form of equidistribution in Q minus R over GCD of QR times gamma mod 1. And of course, if we have no psi weights, we could get some equidistribution by just using discrepancy of the sequence or some similar results. But if we have psi weights, this again becomes a little bit spicy, and we have no idea how to combine the equidistribution in this way with the other SIF condition with the cochromality assumption or something like this. So this is why we are somehow stuck in this problem. If someone has an idea, I would love to hear about it. But this is like the main issue I'm seeing in the inhomogeneous setup here. So on my last slide, I would just like to sum up some of the open questions. Maybe you're eager in solving some of these. That's why I want to put it in the end again. Question number 1 is, can we remove the monotonicity in Khintchine or Duffin-Schaeffer business in the inhomogeneous world when the dimension is small, where we don't know it yet? So if the dimension is big, we know it. If the dimension is small, we know it fails. But there are dimensions in between, which is 2, 1, and also 1, 2 in the non-Liouville case, where we don't know yet. So I expect we could remove it, but it's open. Again, what we talked about a little bit before, we have 2 ways of the inhomogeneous Duffin-Schaeffer conjecture, which means cases mn equal to 1. The weak one only demands the following: if the sum of the phi of q over q psi of q diverges, then we have full measure in the limb subset. This is what I call extra divergence first. This is a little bit weaker than the strong statement on the Duffin-Schaeffer conjecture, where we assume the limb subset of the coprime set to be a full measure. So this would be a perfect dichotomy. But again, I have my doubts, or maybe it's true, but it's very far from obvious that we can prove it. So we have these 2 statements in the inhomogeneous Duffin-Schaeffer business, but we can also ask, of course, about moving targets. Duffin-Schaeffer with moving target holds in dimension m greater equal to 3, and it fails for m equal to 1, but the case m equal to 2 is still open. So we have no idea here, but we don't even know it in the case where the target is fixed but inhomogeneous. So it might be a very tough question to ask here. And again, maybe the most interesting question for most people here, Khintchine with monotonicity, with a moving target, it holds for dimension m greater equal to 2, but in the most interesting case, m equal to 1, this is still open. So if you have any ideas, I would love to work on this or discuss it with any one of you. And otherwise, I would like to stop my talk and thank you all for your attention.
Okay, excellent. Thank you, Manuel. We're pretty much out of time, so let's do a round of applause, virtual or non-virtual. And any quick questions?
Yeah, sure. Can you hear me?
Yes.
Sorry, there seems to be something wrong with my camera. But so do your methods also prove weak and homogeneous Duffin-Schaeffer with moving rational targets?
Yes. Yeah. So I think this follows like this is like a cheap trick because the rationals are countable.
Oh.
So
Okay.
like the way you should go here is just take the rational case. Then this implies the weak rational for a fixed rational has full measure, and now you just intersect countably many sets.
Oh, okay, I see. Now.
Mhm.
So then it doesn't then you get like an approximation for all gamma. No, wait.
But okay.
But this doesn't give you a moving target.
Hmm.
This might be different.
Mhm.
No, I think it doesn't give you what you asked. If the denominators of your moving target are restricted, then probably you can do it. But if it's general, I think it's unclear.
Can't you just use your same proof though, or not?
I don't think so. I have to think about it, but it boils down to this theorem, to this technical one. And I mean, if like you move it, if your target say is moving quite slowly, so that you can accumulate enough mass with the same fixed target, then you can use this. But otherwise, it's unclear. At least I don't see it.
Okay, so wait, you said Khintchine's theorem with moving targets is known in every setting except 1, 1, 1, dimensions 1, 1, is that right?
Yes.
Oh, okay.
Interesting.
That's done in your work or what?
Yes, it's done in our work, but I wouldn't say that this is the first time it was done, because you can already see in earlier proofs that you could do it.
Okay.
So I think it wasn't written down explicitly that you can do it with a moving target, but you can see it in earlier works.
Okay. All right. Thank you. Nice talk, by the way.
Thanks.
Yeah, thanks again for the talk. So please contact Manuel with answers to all these questions as soon as they're around. And thank you again. Let's stop now, and we'll come back in I think in 4 weeks for another talk online. Okay. Thank you, and have a good day.
Yeah, thanks a lot.
You too.